All right, let's pull back the curtain on one of the most important but kind of invisible pieces of technology out there. It's the secret sauce that makes so much of our digital world feel instant. We're talking about hash tables.
So to really get what's going on, let's start with a simple question. Imagine you have a massive list, say 10,000 names, and you need to answer one thing. Is the name Ali on this list? How would you even begin?
Well, the most obvious way, right? You'd probably start at the top, name number one, and just go down the list, one by one by one. But you can already feel how slow that is. In a world that runs on speed, checking thousands of things it's not going to work. It's way too slow.
And that's exactly the wall that early computer scientists hit. They realized that for computers to be truly powerful, they couldn't just search through a giant pile of data every single time. They needed a smarter way. They needed a shortcut.
And the solution they came up with is a truly brilliant process called hashing. You can think of it like a magical postmaster. You give them a name, and instead of thumbing through a giant address book, they just instantly know which mailbox number it belongs to. That's what hashing is. It's the magic trick that turns any piece of data into a simple, direct address.
In an ideal world, the process is just this perfect three-step dance. You take your data, like the name Ali. You feed it into a special mathematical recipe called a hash function, and bam, out pops an index, like the number 2. No searching, just an instant answer.
And the structure that actually puts this magic to work, that's the hash table. At its heart, it's just a bunch of numbered slots, kind of like an array. It uses that hash function to figure out exactly where to put something, and more importantly, exactly where to find it later. The whole goal is what programmers call constant time access, which is just a fancy way of saying it's instant.
Okay, I know what you're thinking. This all sounds a little too perfect, right? An instant filing system for everything? Well, like any great magic trick, there's a catch. There's this built-in challenge that every single hash table has to deal with. So, back to our postmaster. What happens if you give him a letter for Ali and he says, mailbox 2, and then a minute later you give him a letter for Ahmed and he looks at it and says, yep, that also goes in mailbox 2. What do? The mailbox is already full.
This traffic jam has a name. It's called a collision. It's what happens when your hash function, doing its job, takes two totally different pieces of data and tells them to go to the exact same spot. Now, what's really important to understand here is that a collision isn't a bug. It's not a mistake. When you're trying to fit a potentially infinite number of names into a limited number of mailboxes, it's just mathematically guaranteed to happen eventually. So the game isn't about preventing collisions, it's about being really clever in how you manage them.
And that brings us to the really ingenious part of this story, the different ways engineers have come up with to handle these inevitable clashes, without losing that incredible speed we're after.
So there are really two main strategies. The first is called separate chaining, which basically says, okay, if two things want the same mailbox, we'll just hang a bucket on it and put them both in there. The second is open addressing, and its philosophy is, well, if this mailbox is full, let's just go find the next empty one.
Let's dig into separate chaining for a second. With this method, each slot in our table isn't just a single box, it's the start of a little list. So if Ali, Ahmed, and maybe even Assad all get hashed to index 2, no problem. We just create a little chain or a linked list right there at that spot. It's simple and it's really effective.
Now, open addressing is a totally different mindset. Let's say we need to add a new name, and its target slot is already taken. What do? We just probe. We look for the next empty spot. The simplest version of this is called linear probing, which literally just checks the very next slot and then the one after that, and so on until it finds an open space.
But there's a problem with just checking the next slot. You can get these big pileups, these clusters of data that start to slow everything down again. So to fix that, engineers came up with much smarter ways to probe. Instead of just looking at the next spot, they might jump ahead in a more complex pattern, or even use a whole second hash function just to decide how far to jump. It gets pretty clever.
Okay, so we've been deep in the theory, talking about collisions and probing, but why should you care? Well, because this abstract idea is, and I'm not exaggerating, the invisible engine running pretty much your entire digital life. Seriously, hash tables are everywhere. Every single time you log into a website, a hash table is working behind the scenes to check your password securely. When you search a huge database, hash tables make that search feel instant. That high-speed cache that makes your computer feel snappy, hash tables. Dictionaries and programming languages, hash tables. Even the fundamental tech behind blockchain, you guessed it, powered by hashing.
So if you're a developer, why would you pick a hash table over, say, a sorted tree?
Well, it's all about trade-offs. If you need pure, raw, unapologetic speed, nothing beats a hash table. It's O1, it's instant. The price you pay is that it doesn't care about order. If you need your data sorted alphabetically or numerically, a tree is your friend. If you just need to find stuff fast, you use a hash table.
But here's the catch for that incredible speed. You have to keep an eye on something called the load factor. It's just a simple ratio. How many things are in your table versus how many slots are available. If you let that table get too full, collisions go through the roof, and your instant lookups suddenly become a slow, painful search again. The trick is to automatically resize the table and rehash everything once it gets too crowded.
And finally, we have to talk about the fact that the stakes here are way higher than just performance. A badly designed hash function, one that's too simple or predictable, isn't just slow. It can be a massive security risk. Attackers can actually exploit a bad hash function to intentionally cause a huge number of collisions, basically grinding an entire system to a halt.
Which leaves us with a pretty big final thought. We've seen that hash tables are this invisible, super fast foundation for almost everything we do online. But if that whole system hinges on that one little magic trick, that hash function, what happens if the magic fails? What's the real risk of a single, flawed algorithm in a